Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at hashing. So we're doing this for obfuscation. We want to take a set of characters and turn it into complete gibberish. Okay, so how does that differ from the encrypting that we've been doing already? Well, this one won't follow a pattern that can be decrypted by someone with the key. We want to turn this into gibberish so that nobody can decrypt it. So where would this be useful? Well, it's used in things like passwords. So if you have a password for an account, like say at a bank, your bank needs to store those passwords, but it doesn't want to store them as they are, because if someone hacks, they have everyone's password, they can steal your money. Instead, what it does is it hashes those passwords and it stores them as a hash value. That hash value is completely indecipherable. So if somebody hacks and they get all these hash values, they can't do anything with them. If you know the hash value, you can't recover the original password. So that's our goal here with hashing. Now, what the servers do at places like the bank, they have these things called hash tables. They might have millions and millions of entries, and every single time you enter your password, it compares it with the hash table. If they match, you're granted access. If not, you're locked out. So this process of hashing, it takes a message, which is like a password or something like that, and it always produces a fixed bit output. So the output is always the same length, regardless of how long the input was. So one such function is SHA. That hashing function, this algorithm, always produces a 256-bit output. So that means that there are 2 to the power of 256 possibilities of different hash values emanating from this algorithm. So that's a massive, massive number. So it's not like anyone could guess your hash value just by chance. So let's look at a hash value. I call this ridiculously simple hash function, not just because it's nowhere near as complicated as what computers use, but we'll see that it actually causes more problems than it's worth. So for this algorithm that I just came up with, we're going to write these characters using their ASC codes. We're just going to use decimal here because the binary is going to be very long. So the ASC values that you can get from the table, X is 88, at is 64, and this is 52. Just remember to be careful. This is a capital X. An upper and lowercase x have different ASC values. So what we're going to do with this hash function is we're now going to add up these numbers. So when we do that, we get 204. And then we're going to reduce modulo 229. Well, that's actually 204 again. So writing that in hex, it's 16 times 12 plus 12. 12 is represented by C. This will be CC in hex. So because 229 is less than 256, 2 to the power of 8, if I were to write this in binary, it would have 8 bits. We use zeros at the start if there aren't enough digits. So it'll always produce an 8-bit hash, but here is a massive problem with it. If I were to try to now hash this YA2, I would get exactly the same answer. It gives me the exact same hash value. That is called a collision. If we have a function that just adds up the values of the characters, we will get heaps and heaps of collisions. Now this causes a problem. Because the SHA256 function is so complicated though, it makes the chance of a collision very statistically unlikely. In fact, it's far more likely that rather than having 2 different passwords produce the same hash value, you'll have 2 users use exactly the same password. So to get around that, there are a variety of things. There are things you can do to the hash table, like add levels to it, but what a lot of places do is they add salting. So that's when you add a unique string to different users. So if I was at the bank, I would add to this user something like at the start to identify them uniquely, and same for this user here. That would change this hash value and this hash value here. One thing about hash values is if you change any of these only slightly, just like say change just this from an X to a Z, we want a very different hash value. That makes it a lot more secure. So that was a ridiculous kind of introductory example of a hash function. Let's look now at a better one. So for this, I've written it in what's called pseudocode. And what we're going to do is we're going to take this here, which is our password. We're going to apply the algorithm in green to come up with a hash value. So you might be thinking to yourself, hey, what does this mean? We have hash in two different spots. Well, what we do is we start with hash equals 0, we put it into here, and then we sort of update the hash value. This means that our final hash value will be whatever we get for the last step of this algorithm. So firstly, let's convert these to ASC values in decimal. So we're sort of going to hash each of these characters individually. So we start with the hash being 0. So when we put the equal sign into it, the first value of hash, I'll just call it H1, is going to be 0 times 3 plus the ASC value of this character. So that's 61. And we're reducing mod 73. So that obviously gives us 61 mod 73. Now we're going to use this value in the next step. So when I hash A, I'll call this H2. It will be the previous hash value of 61 times 3 plus the ASC value of A, which is 65. So putting that in our calculator, we see that it is 29 mod 73. Now we're going to hash the character 3. So it's the previous hash value times 3 plus the ASC value of 3. And that gives us 65 mod 73. All right, now we're going to hash the final character, which is the Y. So it's always the previous hash value multiplied by 3 plus the ASC value of the character we're up to. And we get there 24 mod 73. So that's our final hash value, 24. Because at each step we reduce modulo 73, 72 is the largest hash value we can have. It's a bit more than 2 to the power of 6. So this will always produce a 7-bit input. We might need to put zeros at the start. So in binary, 24 is 16 plus 8, no 4s, no 2s, no 1s, and of course we would need a couple of digits, a couple of zeros at the start to produce the 7-bit input. So these would often be displayed in the table in hex, so 24 in hex. So we'd have 1 in the 16s column, 8 in the units column. Now we usually write 0B at the start to indicate this is a binary number, 0x to indicate that this is a hex number. So this one here would be more secure and it would have far less chance of collisions than in my previous example. But again, the algorithms used by computers in the real world are way more complicated. They'd be way more secure and basically unbreakable. If you get a hash value, you're really not going to be able to figure out what the original password was. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.